Architect Meera Milan Ajit. She is currently working as a senior architect at L&T Construction, Buildings and Factories. She has worked for various commercial and institutional projects for the Engineering Design Research Centre, ranging from shopping malls, IT parks to metro rails. She has attended many national conferences and seminars. She has also worked as a freelancer in Chennai for various projects.
Welcome to UGC lecture series in architecture. Today I'll be taking you through earthquake resistant architecture, that is AR 6008 lecture 5. In the previous lectures we would have seen what is an earthquake, what are the various causes that cause earthquake, what are the various factors that affect the happening of earthquake, what are the terms and terminologies related to earthquake, what are the what happens after an earthquake strikes, and what are the repercussions of an earthquake. We also saw what are the various criterions that had to be considered while planning an earthquake resistant building. We understood how to choose a site and how to design a plan for an earthquake resistant building. Also, we saw various factors that actually affect a masonry wall, as in a single wall or a combination of walls with roofs and floors, and what happens when earthquake strikes them. So now in this particular lecture we are going to unit 3 part 2, that is building configuration. So before we start, in order to understand the content, so the contents of this particular lecture is building configuration, opening sizes, horizontal reinforcement in walls, vertical reinforcement in walls, inertia forces, seismic load, concept of ductility, deformability and damageability, and how these three words mean a lot to earthquake resistant architecture. Moving on, before we start in understanding building configuration, it's very important to understand why are we going on learning about this particular part in this subject. Every time an earthquake strikes, actually everything gets damaged, and the maximum damage usually caused because of the man-made buildings or the buildings that we construct at in a very unthoughtful manner. Because one building collapse on top of another one, and such a way there is like a lot of buildings collapse on top of each other, that creates a kind of a pile of debris that causes the major damage in the during an earthquake. So it's very important for us to understand the configuration of a building and why a building affect the earthquake, and how to actually regularize that and make something out of it which will not which might have small non-structural damages, but the structural damage will not occur and it will withstand the earthquake. So the first and foremost thing that we'll be seeing today is the building configuration. So the extent of damage to a building depends much on the strength, ductility and integrity of a building, and the stiffness of the ground beneath it in a given intensity of the earthquake motions. So every time a building falls to an earthquake, or it reacts to the earthquake, how well it withstands the earthquake depends solely on the strength of the building as well as the strength of the ground beneath it. So we already saw the site selection and the soil selection and how to go on designing earthquake resistance buildings in firm soil rather than weak soil. So that part of it is covered. We decided on how to choose a site for the building, and that part of it's also covered. Now for the strength of the building, it's very important for us to understand the building configuration and how the building is actually configured and made on site. Almost any building can be designed to be earthquake resistant, provided its site is suitable. Buildings suffer during earthquake primarily because horizontal forces are exerted on a structure that are often meant to contend only with the vertical stresses. So every time a building is designed, that building is designed in such a way that it can react for the vertical forces. But we usually don't design a building in such so that it can withstand the horizontal forces. So that is what has to be kept in mind while designing an earthquake resistant building, because the forces that is going to act on it is horizontal. An important feature is regularity and symmetry in the overall shape of the building. A building shaped like a box, as rectangular both in plan and elevation, is inherently stronger than the one that is L-shaped or U-shaped, such as a building with wings. So every time a building is asymmetrical, or there is a cantilever in part of the building, or there is a cornice that is extending from one part of the building, in earthquake prone areas, that is like A listed in the earthquake prone areas, in such areas it's better we avoid such kind of a construction and go for a much rectilinear and rectangular building which is not too linear, but which has a proper proportion and which is not too linear. If at all we go for a very linear building, it's better we compartmentalize and make it into two separate buildings and making a very linear building, because such buildings are also very prone to giving up during earthquakes. An irregularly shaped building will twist as it shakes, increasing the damage. Next major thing is the opening size. In general, openings in walls of a building tend to weaken the walls, and fewer the openings, less the damage it will suffer during an earthquake. So like we read in the previous lecture, what happens is whenever there is a earthquake happening and it hits the opening of, from the opening of the wall, there is a kind of a diagonal crack that forms on either side of the openings. So such as the number of openings increases, that kind of a non-structural crack can actually occur, and that may weaken the walls of the building further. So it's better to reduce the amount of openings to a certain number than increase the number of openings of a building in earthquake prone areas. If it is necessary to have large openings through a building, or if an open first floor is desired, then special provisions should be made to ensure structural integrity. So next major thing that we will be seeing is horizontal reinforcement in walls. Horizontal reinforcement of walls is required for imparting to them horizontal bending strength against plate action, for out of plane inertia load, and for lying the perpendicular wall together. As I said before, it's usually every building, normal buildings are designed with vertical reinforcement, and in order to withstand vertical forces. So for earthquake resistant building, it's very important to understand that earthquake load happens in the horizontal plane. It's very important for us to give horizontal reinforcement in walls. So in the partition walls, horizontal reinforcement helps preventing shrinkage and temperature cracks. The following reinforcements are very necessary. So horizontal bands or ring beams. So the most important horizontal reinforcing is through reinforced concrete bands provided continuously through all load bearing longitudinal and transverse wall at plinth, lintel and roof level. Also at the top of gables according to requirements as stated. So plinth band. As I said before, it's very important to consider the three major bands and provide horizontal bands in all three major areas. The first and foremost one is the plinth band. This should be provided in those cases where the soil is soft and uneven in their proportions, as it usually happens in hill tracks. It will also serve as damp proof course, and this band is not too critical to be provided. The next one is the lintel band. This is the most important band, and it will incorporate in itself the door, the window lintels, and the reinforcement of which should be extra to the lintel band steel. So it must be, this is a very important band, must be provided in all the stories. The next one is the roof band. This band will be required at eave level of trussed roof and also below or in level of such floors, which consists of joists and covering elements so as to properly integrate them at ends and fix into the walls. The next one is a gable band. So masonry gable ends must have the triangular portion of masonry enclosed in a band. So the horizontal part will be continuous with the eave level band on longitudinal walls. So if you can see in this particular drawing, you can see the lintel band, the roof band and the gable band. So it's very important to give reinforcement in all these three areas. There is plinth band which may and may not, it can be given, it needn't be given. So these three reinforcements are very important and has to be given. Moving to the next one is the vertical reinforcement in walls. So the need for vertical reinforcing of shear walls at critical sections was established, and the critical sections were the jambs of the opening and the corners of the walls. What happens every time in the corners of the wall, when two walls joins, usually the joining of the two walls is not strong enough and it is not adhesive enough, then that area can create a crack, and that can actually cause the wall to topple or fall, and that can also create a problem. So the amount of vertical reinforcing steel will depend upon several factors like the number of stories, story heights, the effective seismic coefficient based on seismic zone, importance of building and soil foundation type. Steel bars are to be installed at the critical sections, that is the corners of the walls and jambs of the doors right from the foundation concrete, and covered with cement concrete in cavities and made around them during masonry construction. This concrete mix should be kept 1:2:4 by volume or even richer. The next important thing that we will understand in this particular lecture is the inertia forces. As I explained the previous lecture, that inertia forces is the major force that actually act when an earthquake strikes, and when every particular section of a building, let it be roof, let it be wall, they will have an inside inertia force that will be acting within it. Those, for example, the roof that is connected to the walls tries transferring the inertia load of that particular the roof to the walls, to the joints at the top of the walls, and the walls that will, if the wall is strong enough and the wall is shear wall, the wall will be able to withstand the inertia and transfer from the roof as well as the self inertia, and will be able to withstand that and not overturn in spite of that. So understanding inertia forces and how that performs is very important in designing an earthquake resistant building. Buildings are fixed to the ground as shown in the figure. So this is the section of the building, and this particular building is fixed to the ground. So as the base of the building moves, the superstructure including its contents tend to shake and vibrate from the position of rest in a very irregular manner due to the inertia of the masses. So when the base of the building suddenly moves to the right, the building moves to the left relative to the base. So as if it has been pushed to the left by an unseen force, which we call the inertia force. So if you can see in here, you can see that there will be a particular type of force that will be acting upon it, because of which the base of the particular building kind of tends to move in the opposite direction, which kind of topples the building, and if the building is not strong enough and not designed to withstand that particular load, it topples. So this particular force is called the inertia force. Actually there is no push at all, but because of its mass, the building resists any motion. So the process is much more complex because the ground moves simultaneously in three mutually perpendicular directions during an earthquake. Here you can see that the ground particularly moves in three different directions during the earthquake, and the building moves in the opposite, sways in the opposite direction, and that kind of causes the usually that is when the cracks or structural failure happen in these kind of seismic designs. The next major thing that we will be seeing is the seismic load. The resultant lateral force or seismic load is represented by force F as shown in the figure. The force is distinctly different from the dead, live, snow, wind and impact load. So every time we design a building, we usually see the live load, the dead load, the snow load, the wind load and the impact load. So almost all of these are the vertical loads. So whatever force that acts as a lateral force from the seismic load is actually a horizontal force, and they are like, that is to be treated very different from the dead load, live load, snow load, wind load and impact load that we usually see for any construction in general. So the horizontal ground motion action is similar to the effect of the horizontal force acting on the building, and hence the term seismic load. So as the base of the building moves in an extremely complicated manner, inertia forces are created throughout the mass of the building and its contents. It is these reversible forces that cause the building to move and sustain damage or collapse. So once a seismic wave hits the building, and the building tends to stay at this particular position because of the heavy weight that it possesses. So that is when this inertia forces is created in every small parts of the building, including the walls, the floor, the roof, everywhere. So when such reversible forces occur, that is when the building tries to move away from the seismic load and tries to sustain the damage or tries to strive from collapsing. Additional vertical load effect is caused on beams and columns due to vertical vibration. Being reversible at certain instants of time, the effective load is increased and others is decreased. The earthquake loads are dynamic and impossible to predict precisely in advance. The important parameters in seismic design. The following properties and parameters are most important from the point of view of a seismic design. So the first and foremost property that is very important in seismic design is the building material properties. This building material properties include the strength in compression, tension and shear, including dynamic effects, unit weight and modulus of elasticity. So these particular properties of building material is very important in deciding the seismic properties of a building. Another major factor that affects the parameters in seismic design is the dynamic characteristics of the building system, including periods, modes and dampings. And the third and the last one is load deflection characteristics of building components. Now we will be seeing the concept of ductility, deformability and damageability, and how these particular factors affect a seismic design. So desirable properties of earthquake resistant design includes ductility, deformability and damageability. Ductility and deformability are interrelated concepts signifying the ability of a structure to sustain large deformations without collapsing, and damageability refers to the ability of a structure to undergo substantial damage without partial or total collapse. So in case of a very severe earthquake, there will be like very intense damage. So how much can a building withstand that intensity of a damage and yet not collapse is what damageability talks about. So this is desirable because it means that structures can absorb more damage, and because it permits the deformation to be observed and repairs of evacuations to proceed prior to collapse, and in this sense a warning is received and the lives are saved. So first we will talk about ductility. So formally, ductility refers to the ratio of the displacement just prior to ultimate displacement or collapse to the displacement at first damage or yield. So basically, once the earthquake hits, it will have an initial displacement, and then for a fraction of a second, and then only it will collapse. So what is the ratio of displacement of that to this is what we call ductility. So some materials are inherently ductile, such as steel, wrought iron and wood, and other materials are not ductile, that is brittle, so such as cast iron, plain masonry, adobe or concrete, and that is they break suddenly without warning, and it won't give us a warning to escape from there, and it won't sustain for a while and then fall. So such materials are ductile, and the ones which without warning falls off are not ductile. So brittle materials can be made ductile usually by the addition of modest amount of ductile elements such as wood elements in adobe construction or steel reinforcement in masonry and concrete constructions. So by adding ductile materials to non-ductile elements, we can make the non-ductile element more or less ductile, and that is what is very important in designing buildings for seismic to withstand seismic loads. So for these ductile materials to achieve a ductile effect in the overall behavior of the component, they must be proportioned and placed that they come in tension and are subject to yielding. Thus, a necessary requirement of good earthquake resistant design is to have sufficient ductile materials at points of tensile strength. So, wherever there are points of tensile strength, we should provide sufficient ductile materials there in order to make it seismically well designed. The next factor is the deformability. Deformability is a less formal term referring to the ability of a structure to displace or deform substantial amount without collapsing. So, besides inherently relying on ductility of materials and components, deformability requires that structures be well proportioned, regular and well tied and are avoided, and forces are capable of being transmitted from one component to another even through large deformations. For example, like we have to, when there are when a roof is connected to the wall, the adhesiveness of the wall to the roof should be intact, so that the roof will be able to transfer the loads to the walls based on the strength of each walls. Such openings can be avoided much in the facade, or the plan can be proportional or rectangular and non-linear, and such small factors can actually help the building to actually have a better deformability factor than relying completely on the ductility factors which is inherent in a material. So, ductility is a term applied to material and structures, while deformability is applicable only to the structure. A structure can be ductile, a material is ductile, but only a structure can be deformable and a material can't be deformable. So, even when ductile materials are present in sufficient amount in structural components such as beams and walls, overall structural deformability requires that geometrical and material instability be avoided. That is, components must have proper aspect ratios, that is not to be too high, must be adequately connected to resisting elements. As I said, everything should be the adhesiveness of each material to each other should be high, each component to each other should be high and must be well tied together. For example, positive connection at beam seats so that the deformation do not permit a beam to simply fall off a post, so as to permit larger deformation and dynamic motion to occur without sudden collapsing of the building. And the last thing that we will be discussing in this lecture is the damageability. Damageability is also a desirable quality for construction and refers to the ability of a structure to undergo substantial damages without partial or total collapse. It's a very similar term of deformability, and a key to good damageability is redundancy or provision of several supports of key structural members such as ridge beams and avoiding of central columns and walls supporting excessive large portions of a building. A key to achieving good damageability is to always ask the question, if this beam or column, wall collection, foundation, etc. fails, like what is the consequence of that? What if this fails? What will happen after that? So, every time that question is asked, each and every element would be designed such that if this happens, the other one will withstand the load. So, if the consequence is total collapse of the structure, additional supports or alternate structural layouts should be examined, or an additional factor of safety be furnished for such critical members or connections. So, basically it is very important to use ductile materials in a seismic design building. It is very important to add ductile materials to non-ductile materials to make it almost ductile. It is very important to create an overall deformable, non-deformable structure by considering the plan, the shapes of the plan, the proportion of the plan, the size of the building, the height of the building, and the various factors that affect that. Also, it's very important to give the desirable quality of construction and additional factors that can actually help the building to perform better in the damageability factor. Moving on to the summary. In this particular lecture, we saw the building configuration and its impact on seismic resistance, and that is discussed and understood. We understood how a building configuration, wall openings, etc. kind of help building withstand seismic loads and help it perform better in earthquake conditions. So, horizontal and vertical reinforcement in walls are discussed and their implications were understood. So, why usually we go for vertical reinforcement? What are the most important reasons why horizontal reinforcements are required? Why, along with consideration of dead load, live load, wind load, etc., we should also consider seismic loads and create horizontal reinforcements in the building? And the concept of inertia is discussed, and why inertia is important in this seismic designs is understood. The seismic loads were discussed in details and understood, and the concept of ductility, deformability and damageability is discussed in details and understood, wherein we understood that it is very important for a material, the materials in the buildings to be ductile, and the building to be overall structure to be deformable, and the deformability factor and the damageability factor in such buildings to be higher. So, moving on to the questions. How does building configuration and opening size impact the seismic design? What are horizontal and vertical reinforcement in walls, and what are their implications? Elaborate. Explain in detail the concept of inertia. What are seismic loads? Elaborate. Define the concept of ductility, deformability and damageability in seismic design. So, in the coming lecture, we will be seeing how each type of building respond to earthquake loads. For example, how does a masonry building respond? How does a wooden building respond? How does each material in a building react, and how such kind of construction respond to earthquake or seismic loads? Thank you.